Welcome student. Today we are going to discuss PCH 4802 unit 3 in which we are going to discuss today, that is alkene synthesis. I am Dr. Devangar Pandya from Department of Chemistry, St. Xavier's College Autonomous, Ahmedabad. Well, the points to discuss in this lecture. First one is synthesis of alkene by elimination reaction, alkene synthesis by Witting reaction with stabilized yields, and application of Witting reaction. And in last, we're going to discuss dynes by Witting reaction. Let us begin with the synthesis of alkene by elimination reaction. As you know, alkenes can be made by the dehydration of alcohol. Here the structure 2 is given, and on dehydration of structure 2 we're going to get structure 3, that is the alkene. That way we will going to get the alkene by dehydration of alcohol. Usually under acidic condition this dehydration proceeds, the alcohol being assembled by the usual methods. That this route particularly good for cyclic alkenes, like you can see the structure 3. The cyclic alkenes we can obtain by the dehydration of alcohol in acidic condition. uh, uh, on the other hand, we have those compound made from tertiary and or either bicyclic alcohol. We need to use even mechanism. That is, elimination reaction works there very well. The same alkene is formed from structure 2, regardless of which side eliminates from elements and gives structure 4. uh, that structure 4 gives a 76% yield of and 80-20 ratio mixture of structure 5 and structure 6. 2 alkene is going to be obtained using this method, even or elimination reaction. Acid must be fairly strong for this job and must have a non-nucleophilic counter ion to avoid substitution reaction. That is the condition for this type of elimination reaction. I repeat, the condition for this type of elimination reaction in which acids must be fairly strong for this elimination and must have a non-nucleophilic counter ion to avoid substitution. Now, popular ones here, those acids in which we can take uh, for potassium bisulfate, tosyl hydroxide. These are the compound crystalline and easier to handle than H2SO4 or S3PO4. We can use KHSO4 and TSOH. And the less acidic POCl3 in pyridine, that also we can take here for this elimination reaction. Little control is found over the position or geometry of the alkene, though in many simple cases, such as we have the example of molecule 2 here, this does not matter. Notice, however, if we have alkyl group instead of that substituent R, very little exocyclic alkene is going to be obtained, if any is among the product. Well, when Zimmermann and Keck wished to study the photochemistry of a series of alkene of the journal, as you can see here, structure 7, which have the substituent group, phenyl group are there. So for this structure 7, they could have put hydroxide group at either end of the double bond, but they chose to break the point from point 8 phenyl group, because dehydration of tertiary benzylic alcohol should be very easy and there is no ambiguity in the position of the alkene. Whatever alkyl group or substituent group you may take, they use the Grignard method and dehydrated structure 8 with POCl3 in pyridine. Well, here in this example, elimination of alkyl halide follows essentially the same strategy except that the reaction is now done by E2 mechanism with a strong hindered base to avoid SN2 reaction mechanism. This approach is good for terminal alkenes like we have the structure 10, as the elimination is successful on primary halides. The alcohol structure 12 can be made by any method. So a typical synthesis might involve treating the alcohol 10 with tribromophosphorus to make this bromide and eliminate with tertiary potassium butoxide. That is the strategy. There is again no ambiguity in the position of alkene. Well, dyes can be made by this elimination strategy if vinyl grignards are used, as vinyl group blocks dehydration in that direction and make the cations intermediate with the E1 reaction allylic. And an interesting example we can take here is the four-membered ring. You can see here structure 13 disconnected via the allylic alcohol, that is in, you can see in structure 14, to cyclobutanone, that you can have here as a structure 15. This cyclobutanone, that is structure 15, is available and also very electrophilic. So addition of vinylic grignard and dehydration with the rather unusual reagent like iodine gave the diene, that is structure 13. This diene is used in Diels-Alder reaction, uh, which you have already studied in any other standard semesters. Now let's study the alkene synthesis by Witting reaction. We're going to compare it with elimination method as well. The most important method of alkene synthesis is a Witting reaction, which gives full control over the position of double bond. That means this reaction is stereospecific reaction and some control over the geometry as well. So a phosphine, usually triphenyl phosphine PEH3P, react with an alkyl halide. This type of reaction is assigned two type of reaction to give a phosphonium salt. You can see here structure 18. Treatment with base of the base which we are going to use here, that is butyl lithium, and it always gives the phosphonium yelid. Yelid is a compound which contain both positive and negative charge in simultaneously in the same molecule, and that is structure 19. And yelid is a species with positive and negative charge on adjacent atom. So that compound is called yelid. Here structure 19 is yelid. Reaction with an aldehyde gives the alkene, and usually this kind of alkene is the Z alkene, Zisman alkene, that you can see here structure 20. And if you are taking here R1 substitute group as an alkyl group, the triphenyl phosphine oxide is going to be obtained. Now we can see the mechanism part in the lower second reaction as well. The mechanism for the formation of alkene is often to discussion, especially as there is no agreement on the source of stereochemistry. We suggest the carbanion end of the yelid adds to the aldehyde, that is structure 22, and betaine then cyclize, that gives structure 23 to the four membered ring, which has the fragments to give the product 24. There is no doubt about intermediate structure 24, nor that its decomposition must be stereospecific. So Z, the alkene that you have seen earlier reaction, that is structure 20, is formed from the cis phosphatane, that is structure 24. Now another example of Witting reaction, as the Witting reaction forms both pi and sigma bonds, this connection is right across the middle of the alkene, give a choice of starting material. So with the exocyclic alkene that you can see in structure 26, that is the exocyclic alkene, a very difficult to make by this elimination method. So here is the comparison that when the restriction is there for elimination reaction, you can use this Witting reaction to get the desired product. We could use formaldehyde or cyclohexanone as the carbonyl component with either phosphonium salt, that is structure 25, or structure 28. It is a matter of personal choice whether you draw the yelid, the phosphonium salt, or the alkyl halide in this stage. Witting did this synthesis with the iodide, uh, that is 29, which he made himself to give 26 structure in low yield, that is 46%, but higher yields are routinely obtained. Nowadays the scientists are obtaining more and more yield out in this reaction. Vogel reports that 64% yield can be obtained from the commercially available bromide, that is structure 30, using the sodium salt of DMSO as a base. Well, a tri-substituted alkene, that is structure 32, are notable as either a secondary halide, that is structure 35, or a ketone can be used. Both these 33 and 35 structures are available, and we can choose them, uh, and we can proceed the reaction. The synthesis is straightforward, but does produce a mixture of the geometrical isomers over here. This is another case where dehydration even of the tertiary alcohol, you can see in the reaction, that is structure 36, would probably give a mixture of position and geometrical isomers. Witting reactions with stabilized ylids. The unstable aspect of the yelid is the carbonium phosphonium salts are stable compound. So any substituent that stabilize the anion also stabilize the yelid, and this reverses the selectivity to for favor the E alkene, that is antigen alkene, E isomer. Even benzylic ylide give E-isomer or E-alkene, as in the reaction with the anthracene, that is you can see here as a structure 37, that give a good yield of crystalline product, that is 38, having a coupling constant between the two marked uh, HS of 17 at Z. So one possible explanation is that the formation of the betaine or oxophosphatane is reversible if the yield is stabilized, and only the faster of two elimination occurs to give the antigen alkene. Here you can see the yield 74% is obtained by this method. Now applications of Witting reaction. An excellent application of the distinction between stabilized and unstabilized yelid is in the synthesis of leukotriene antagonist, the intermediate, that is structure 39, where R is a saturated alkyl group of either 6, 11, or 16 carbon atoms was needed, and disconnection of the Z, that is Zusammen alkene, one of its isomer, with a normal Witting reaction in mind, followed by removal of epoxide, exposed a second alkene with the E configuration, that is anti-Jason configuration that could be made from the aldehyde 43 and stabilize the yield, that is structure 42. Now this yield is so stable that it is commercially available and reacts cleanly with structure 43 to give only E isomer, that is structure 41. Epoxidation under alkaline condition gives the trans epoxide, that is structure 40, and a normal wetting on unstabilized yield gives 39. The yield depends on the substituent group R. When the substituents becomes very anion stabilizing, as you can found here in the structure 42, the yield may not react with the ketones and anions of phosphonate esters are usually preferred in the Horner or Wordsworth anomalous, that is HWE variant. The reagent triethyl phosphonoacetate, that is structure 46, is made by combining a phosphide, that is triethoxyphosphide instead of a phosphine with ethyl bromoacetate. Displacement of bromide, that is 44 structure, gives a phosphonium ion that is dealkylated by bromide, that is structure 45. Barrett, used the reaction at the start of his synthesis of an antibiotic compound. The HWE reaction with the NL, that is 47 structures, gives the diene ester, that is 48, and by reduction of diol the dionyl 49 is going to be obtained. Further in application, we have the example of the optical brightener, which is known as palenyl, that is structure 50 over here. It makes your clothes looks whiter than white, and your t-shirt fluorescence in UV light can be disconnected by the wetting strategy to two molecules of the phosphonium yield, that is 51, and one of the dialdehyde, that is structure 52. The availability of dialdehyde used in this manufacture of pteryline can make this route preferable to the alternative strategy. As the yield 51 is stabilized by the nitrile as well as the benzene ring, the phosphonate ester, that is structure 54, is preferred in the manufacture and the reaction is strongly trans-selective. The byproduct is the anion of dimethyl phosphate, that is structure 55, which is water soluble and very easy to separate from the product 50. By contrast, triphenyl phosphine oxide is insoluble in water and can be difficult to separate from the alkene. Another example of this wetting reaction application includes pheromones. Pheromones, that is insect attractor, or the compound which attract insects. So many insect pheromones are derivative of a simple alkene. This perler, that is structure 56, and attractant for the gypsy moth is an epoxide derived by stereospecific epoxidation from the Zussman alkene, that is Z isomer of alkene, that is structure 57 over here, as neither substituent is anion stabilizing. A simple wetting should give the right geometry. The synthesis was carried out this way, though no doubt the alternative combination would also work well here. The synthetic material is as attractive to the moth as the natural pheromones. Now last point, that is Dines by Witting reaction. In this Dines by Witting reaction, the conjugated dienes are needed for the Diels-Alder reaction, and Witting disconnection, that is of structure 61, reveals that the choice here are more important. The easily prepared anols, that is 62, would react with the unstabilized yield, that is structure 63, to give a Z isomer of alkene, but the conjugated allylic yield, that is structure 60, might give the E isomer of alkene. So you can see in this reaction the Z and E alkene is going to be obtained by this process. So two pathways are there. The mono substituted butadienes, that is structure 66, was needed with a trans alkene in the middle. So this connection using track A, that is 60A, looks good, and the allyl phosphonium salt, that is structure 65, did indeed gives E isomer, that is structure 66, though in a poor yield. These low molecular weight hydrocarbons are difficult to isolate as they are volatile in nature. Now diaryl butadienes, that is structure 69 here, can be made by the second route, that is 61B method. As the yield in the previous slide, you can see that is the structure 68 is conjugated and will give only one E isomer of alkene, while the other outcomes from an aldol condensation used to make the anal. Though the Witting is the most important, there are many other ways to make alkene using a variety of elements in the periodic table, keeping the same disconnection in mind. Well, that is enough from my end. Students, thank you very much for paying attention to this video lecture. I always inspire students to ask question. Keep asking question. As you know, asking question is a beautiful way to gain knowledge.